So today I would like to present to you the results of an ongoing project aiming at constructing a method for automatic classification of pottery profiles. This project is a collaboration between myself and Dr. Monika Syga from the Warsaw University of Technology, who is kind enough to be with us here today. She's the mathematician in this, I'm the archaeologist. And first of all, let's talk about the motivation that led us to taking up this question, this problem. So pottery on the majority of sites, pottery is the most abundant type of finds. And those with you dealing with pottery know that it can go into hundreds of thousands of fragments, even in one season. So the traditional way to handle such big assemblages, such big amounts of pottery fragments, is to create site-specific typology and then see how this typology relates to other sites and how it fits into the regional patterns of pottery production. Such typologies are usually done manually, and often they depend heavily on the specialist's knowledge and his experience. And this makes them prone to subjective biases, oversimplification, or authoritative decisions about the specific groups of pottery. And this process suffers from the large amount of data, the data that has very subtle changes sometimes between the groups. And we have problems, issues like inconsistent terminology, often between the sites or the regions. So this all made us think about constructing a method that would allow us to investigate ancient ceramics through the shape of those pots. And the proposed method is meant to work on rotationally symmetric vessels, preferably the ones made that are wheel-made because they have a consistent shape. When we get into non-symmetrical vessels, this gets a lot complicated, so we're not dealing with this for now. We aim at detecting similarities in a given set of vessels and generate a typology through automated or semi-automated analysis of the shape. And we applied different descriptors. I'm going to talk about this a little bit later in the presentation. Something that was really important for us in the whole to apply to the method was that we could include the expert's knowledge. This cannot be done fully automatic. It has to include some prior knowledge about the investigated pottery, about the investigated assemblage. So just a short comment, what actually is classification? In archaeology, the way we understand it is grouping pots according to their shared features, whether it's shape, function, type of fabric, color, or decoration, or even production technique. All of these features can be combined to produce sort of a grouping, a categorization of the pots that we're dealing with. This is mainly based on microscopic observation or microscopic tube for the fabric, but this is more rare, and measurements. And this typology and distinction of those features is very often vital to establishing the relative chronologies, the function of the excavated areas, or connection between site and regions. And I think this plays well with what Henry said before. This is what you can do if you have good topologies, you move on to larger scale problems. However, in mathematics or computer sciences, in a formal way, creating a classification, a typology, as we call it in archaeology, starts with finding a way to describe the investigated objects in a way that allows computational analysis. We have to define similarity, so we have to think about what it means for us that something is similar or is this similar. Next, we have to find, of course, a way to measure this predefined similarity. Next step is easy. You establish relations between the specific objects in a set in order to create specific groups of objects that we can later investigate. Okay, so classification can be done on a number of different features of the vessel. Like I said, it can be also done on different representations of those features. In the computer sciences, we can find a way, even if we have one feature of the pod, we can represent it in several ways. In our investigation, we have focused on the shape, as this is one of the most informative features of vessels that allows us to analyze everything else, like its function or where it came from. So at the same time, shape is very hard to define in a formal way, because when describing pottery in archaeology, we often use descriptors like oval, elongated, flaring, or some quantifiers, slightly, heavily flared, combination of those, or even comparisons like bell-shaped. All of this is very natural in written or spoken language. It's widely understood. However, translation of this into a formal language is very elusive, very hard. So we decided to work on profiles of the vessels as they're a graphic representation of all the attributes of the vessel. We don't need to tackle the terminology issues here. They're a widely accepted standard of documenting pottery, of conveying shape, and they allow wide comparison because we have published material from other side. If we have our profiles, we can easily match them to the already published material. It was also very important for us that this is kind of documentation that is done, let's say, anyway. It's done on every project, so it's already available to us, and there is no need for an extra step to prepare the data for our analysis. We already have it in a regular process of documenting excavation. Pottery and the ways to investigate it through computerized methods in order to enhance this analysis or facilitate it or speed it up are very widely investigated, especially in the couple of the last years. And with the introduction of 3D scanners, this is all very promising. However, we decided to focus on the two-dimensional data because we believe that it can be integrated into the workflow with 3D-dimensional data, but this method needs to be perfected, and then we can apply it to the data that will be available to us. So shortly, I would just describe the input data we have. This is actually just a general representation how we get a profile. Our profile are in the forms of bitmaps in black and white. We extract a contour, and then the contour of the profile is transformed into a curve, which is saved as a set of points, of two-dimensional points. Yeah, and one thing, the important requirements for the methods are that the images have to be in the same scale and the same resolution and have to have the same orientation, because as we bring them into the method, we have to have a guarantee that when we match two images, they are in the same scale, that we don't need to introduce another variant here in the method. So as soon as the profiles are in the form of vectors, we can actually perform different analysis using different shape descriptors, and we have chosen two shape descriptors here, the dynamic time warping and procrustes analysis. I will describe those methods very shortly. We're hoping to publish an article very soon, so hopefully you will have all the formulas and details of the methods there. The dynamic time warping method is a method that derives from signal processing. It's somewhat akin to the fresh head distance, and it's also been called the dog on the leash type of distance. So to explain this, you have to look at the image on the top and imagine a man walking his dog. Both of them are walking different paths, and these paths are actually the curves we are working on, and the dynamic time warping, or the fresh head distance, is the shortest possible leash that will allow the dog to walk with his owner at the same time. This method basically calculates the cost of transforming one curve into another, which you can see in this image here. They don't need to be of the same length, but this method works well with curves of a similar length. It doesn't deal very well with curves that differ drastically in length. So the second method we used was the Procrustes analysis. So Procrustes is actually a name of a mythological figure. Awesome. He was called Procrustes or Damascus. He was a bandit from Attica, and he would lure travelers into his home and torture them by making them fit an iron cast bed he had in his house. So the way he would do that was by stretching them if they were too short, or cutting their limbs if they were too long, too tall. I'm sorry for that morbid detail in the morning. But anyway, this method is a shape matching technique, and same as Procrustes did, it uses rotation, scaling, and transformation to detect similarity between complex shapes. So we have, this is actually an example from biology. These are wings of a dragonfly viewed in different positions. So we use scaling, then shifting, rotation, and translation to fit the shapes as well as possible. However, this method does never fit the shapes exactly. You can see in the end we're left with two similar shapes, but they do not overlap. So this method is really good for a more robust matching. Moving on to the method we proposed. This is the scheme we use in our work. So first of all, we have the data preparation, as I said before. And first of all, we use the Procrustes method. In this method, one profile, let's call it profile B, is to transformed in such a way that it best matches profile A. This is this transition. So you can see in this case, it was mostly scaling. Very often we deal with rotation. Translation is not really common because we deal with that, assuring that all the images, input images, are oriented in the same way. But scale is an important factor in the analysis, and orientation can tell us if the shapes are, one shape is more open, one shape is more closed. We can detect this in this step. So the factors of scale and rotation are embedded in the method. We have them, this is one of our measures of similarity. And in the second step, we use the dynamic time warping method to actually calculate the distance between those, in this step, because between the profiles that have been best matched in a general way. Yep. This is the result, and we can get different types of classification this way. We can have a more robust one. We can have a classification that's oriented more towards very subtle features of the pots. This is just to show you, it's a small data set that we have been working on. This is Bronze Age Minoan pottery. It has been already published in general publication. Most of this comes from Knossos. You can see clearly delineated the groups we have here and how they perform, how the method performs on this set. There is some variability, especially the little guy here, number one. He's been, well, not actually misclassified, because we choose a dendrogram to represent the results. And as you can see, you can cut the dendrogram tree at any of the points. Any of the levels. So we have a more general classification, but if we cut it at a lower level, we get a more detailed classification of the pots available. For each step of the process, we can assign weights to the Procrustes analysis, to the dynamic time warping. We can assign weights to specific aspects of the Procrustes analysis. So we're, for example, more interested in the relations of scale between the vases. We can assign that weight to make sure it's embedded in the method. And as a part of our goals for the future, we definitely want to make this method work for fragments of pots, because for now it works only for whole profiles, and fragments are, abandoned on every excavation. So this is our goal for the nearest future. We would definitely love to test this method on a seriously large data set. We're thinking maybe 500, maybe 1,000, to see how it performs on really large data sets. And we believe that the method presented here will facilitate the study of large data sets, large assemblages, It will allow an initial analysis of comparison between sites or a study of regional variability of pots. However, in the whole process, the expert knowledge is necessary. It needs to be embedded in this. And this is just a tool to facilitate the analysis of really serious amounts of data.